my screen?
Not yet. Yes, I can see it now.
You can see it. Okay, good. Okay. Um, so you see this thing called a function, right? It's a very, I think it's probably one of the basic concepts when it comes to what some people call additional maths, like a step above basic maths. So I don't know whether, yeah, additional maths or further maths or something, because it's based on this concept that other concepts like calculus, differentiation, integration, all those things are built on it. So, like, understanding it is really, key. And the good thing is that it's quite simple to understand. So, if we come against that background, we can now um, take a look at what it's all about and be comfortable with it. So, well, this definition is quite straightforward. A function is a special type of relation. Okay. A relation is not nothing really more than an equation that an expression, usually a mathematical expression that shows a relationship between at least two variables. Okay, usually two variables. Now, when I say relationship, so addition, subtraction, multiplication, division, order. And when I say order, that means like raised to power two, usually two, three, that kind of thing. uh So those are
So
the
those are
things that you would find on the right hand side of a function. And when I mean right hand side, that means you will definitely have a left hand side and a right hand side. Usually the left hand side is where is the single variable that is, if you like, you can call it the subject of the formula. Okay, but let's not get ahead of ourselves. So it says all functions are relations. Yes, because they show a relationship between one variable, usually called the independent variable, and then the second one, usually called the dependent variable. The one outside on the left hand side is dependent on the one inside. Why? You can even see it. Anything you put in the right hand side, by the time you crunch the calculation, do all the addition and subtraction, the answer, the final answer will be what the value of the one on the left. So that's why you have them, you can call them a relation. Now, it now says, but not all relations are functions. Okay, so we'll see why that is. So it's a function. I think this one is a more embracing rule. It's a rule, definition rather. A function is a rule that maps an input to a what unique output. It maps an input to a unique output. So um, let's see um, from these diagrams which ones are functions. So the first one, uh, if you can see, there's only one line between one dot in the input side and one dot in the output side. Um, and that is agreeing with the definition, an input to a unique output. Now, the if you look at the second one, it appears that two different inputs have are being mapped to a particular output. So, well, it still passes the test in a way. Um, so we have separate inputs, and sometimes two of those inputs can be mapped to one output. This kind of let me give you an example of this kind of function. Let's say you have a function that says y equals x squared. You remember that um, if you raise a negative number to power 2, that's you square it, the answer you will get is the same as raising the positive version of that same number to power 2. So for instance now, minus 2 squared and 2 squared are the same. Okay, so that can tell you that the minus 2 and plus 2 are the input. The 4 that both of them map to is the output. Okay, so in that case, the function is simply y equals x squared, which shows the relationship between x and y. So that's why it's called a relation in that sense. Okay, so now let us see some cases where we cannot call it a function per se. Now, look at number 3 very well. You would see that in number 3, one input is being mapped to 2 different outputs. Okay, so what would be an example of this? An example would be a function that says y equals square root of x. Y equals square root of x. In that case, let's see where it violates the definition. The definition where it says a function is a rule that maps an input to a, not several unique outputs. So that's where number 3 violates the definition. I don't know if you understand what I'm trying to say.
Yeah, I get you.
Okay, so that's why I'm trying to use examples. So again, the example for number 3 of something that is not a function, because it violates that definition, is the function that says y equals square root of x. And if you check it, you can see what I'm saying. Y equals square root of x. So let's pretend our x is 4. Square root of 4 is what? Plus or minus 2. Because of the existence of those two possible outputs, we cannot say that that is a function. But guess what? If we tell ourselves that the input is a set of integers, positive integers, and the output is also a set of what? Positive integers. That's the y, the side that is the answer, the y. You see that we have now exempted some set of numbers, which means we have left out the negative numbers. So in that case, based on the definition of the sets where the values are coming from and going to, we can say that that is a function. So what I just said now with that small demonstration is that even something that may fail to meet the definition of a function in one sense can eventually be seen as a function under different conditions when you exclude certain numbers. But I think another example will suffice. So let's keep going. Let's look at number 4. The problem with number 4 is that it leaves out some input. Again, look at the definition. A function is a rule that maps an input to a unique output. So that's why you can see one of the inputs is left. Okay. Now, on the other hand, look at number 5. Number 5 maps all the inputs to a unique output. But then there are some there are some values in the set for the output that don't have any input mapped to them. That one is allowed. Why? Because we are still working within the parameters of the definition that a function is a rule that maps an input to what? A unique output. It doesn't say that all the outputs will have mappings from the input, but it's saying that all the inputs will be mapped to a unique output. Okay, so now that we have that um, registered, let's see um, some other concepts that we need to talk about here. Now, that thing that you see there that they said input domain, that tells you something. A domain is, well,
Mm.
basically like a set of numbers, right?
Mm.
A set of numbers. So if you like, you can say a set of integers. I think they usually use Z to denote it, a capital
Mm.
letter Z, just like set of natural numbers. Set of natural numbers starts from 1, 2, 3, 4 to infinity. That also can be classed as a domain. Okay. Now, of course, the output will also be a domain too. So it depends. Sometimes um, when you carry out some operations on integers, you will always get an integer. So yes, that is granted. But there are sometimes that you carry out operations on an integer, and the result it can have decimal point. Once the result can have decimal point, guess what? It means that the output, what you are calling the possible outputs, the the possible outputs may include decimal points. So it will not be the same as the domain of the input. So in that case, you have different domain for inputs and different domain for outputs. Okay, so what are they trying to say here with this um, smaller rectangle inside a bigger rectangle? What you call the range are the set of numbers that have an input mapped to them. Okay, now remember that we said that it's possible that some numbers in the set of the domain for the output may not have anything from the inputs mapped to them. Yes, it's still a function. So how do we differentiate them? You can just say that the codomain, or the one that embraces everything, okay, is the one that is all inclusive, whereas the range is strictly the numbers in the codomain that have an equivalent number from the input domain mapped to them. Okay, so let me give you an example for this one. Let's say, let me see if I can quickly cook up something here. Y equals x over 2. Y equals x over 2. Okay, so now let's just look at that function. That in itself is a function, and I can show you some examples of it. Now, let's look at a value like, let's say x is 10. In fact, okay, maybe we could even start from 1. 1 x over 2, y equals x over 2. X over 2, the first value, if you think of x as the set of natural numbers, x being the input domain, the variable representing the input domain. So we'll pick from there. You always take note. You start with an input and end with an output. Okay? You start with an input and end with an output. And it's as simple as substitution. That's how simple it is. That's why sometimes it looks like concepts like this, people miss it because maybe because the introductory stage was not well explained or something. I don't know. But by the time you see all there is to functions, you will see that there's really nothing, nothing so special about it. Okay. So like let's just push my example a bit. Y equals x over 2. X is the variable representing, remember, independent variable representing the set of natural numbers. And set of natural numbers starts from where? 1, 2,
Mm.
3, and so on and so forth, right? We're not dealing
Mm.
with 1.5, nothing in between. Okay, so once we have that at the back of our mind, we can now know what to expect. Now, I want you to take note. Look at what will come out on the y side. The first value for y is what? That's 1 over 2. And we all know that 1 over 2 is not a natural number. It is, what do you call it? You can think of it as a rational number. That is like you can express it as a ratio. So it's not natural in that sense. It's a ratio, rational number. Or you can see it as decimal. Okay, so that's 0.5, isn't it? And because it's 0.5, it means it now falls into the set of what? Real numbers. Okay, so now remember that real numbers involves integers, decimal numbers, um, all the things in between. Well, you understand, so it's and of course it also involves the negative numbers. Did you notice that set of real numbers also involves negative
Mm.
integers, negative decimal numbers? So what do you think will happen? That kind of example is a perfect example of what happens here. So the very first number that can come out from y equals x over 2 is what? 0.5. You know what that means? It means that it has left out 0. It has left out 0. It has left out all the infinite numbers between 0 and 1. And trust me, you can't even list all the numbers between 0 and 1. If we start now, we can't list all of them. You'll be thinking, is it not just 0 and 1? No, between 0 and 1 is so many numbers that you can't list. Okay. Now, it has left out all the negative numbers. I don't even want to talk about the negative integers, negative decimal numbers, negative. Remember that you also have irrational numbers, the ones that you call recurring decimals. Those ones are there. They are in their own set, in their own area. All those ones come under real numbers. So in other words, what will you now call the range for that particular um, function y equals x over 2? Simple. The range will be this. The range will be, because the implicit domain is set of natural numbers, and the range is the ones that will map exactly to each individual one. Then you can say that the first natural number being 1, by the time it goes into the function x over 2, the number that comes out on the left-hand side is what? 0.5. Now, please follow me on the left-hand side. I'm not talking about on this diagram. On the left-hand side is I'm talking about on the, maybe I should do a bit of illustration here. Y equals x over 2. Okay. So I said where we always have to define things now. We can't just assume anything. X is an element of natural numbers. And of course, we've established that for this thing to be realistic, Y will be elements of real numbers. Okay. And then take note that it's not all the real numbers that are even covered. Okay. So let's see where it is. So they can give you something like this and ask you, what is the range, right? What is the range? What is that subset of the codomain that the function really maps inputs to? So you can look at it this way. The range will be, now, how do we get the range? So that's what we want to do now. The first thing here, they may not ask you, but at least for your own understanding of this, let's just do this as an exercise. So since X is set is elements of natural numbers, the very first what will I call it? The very first element in the range will be what? So you may want to know. So you say, okay, what is Y? X is what? Where X is 1. 1/2. You can just say this is equal to what? 0.5. So what this means, following that our diagram, right? What this means is that if these are the inputs in, and these ones are the outputs out, then where you have 1, X is 1, it's being mapped to what? 0.5. Okay, so like I said, this starting from 0.5 has already left out so many things, right? So the range, um well, the range, I can't even really say that it's um yeah. So the range is going to be like, you can think of it as a set that starts with what? 0.5 followed by what? And you can think of this is so like when you want to plot a graph, right? When X, you have a table for X and you have a table for Y. You can also come up with that concept. I think it's even more straightforward like that too. And you have X and Y. X is 1. Remember, natural numbers. Excuse me. 0.5. Okay. Then the next value of X is 2. 2/2 is 1. So that's 1. Can equally say 1.0 since 0.5 is already in the picture. So we can put a 0.0 behind it. And when X is 3, 3/2 is 1.5. One whole number, 1/2, which is 1.5. So you can see how the thing is forming. These are the numbers that you would say are in your range. Now, so that's how I'm going to write them nicely. And nobody is expecting you to give them everything that will be in the range. So you can just put dot, dot, dot. At least you have established that you know what is happening there. So this is the range. Now, so uh, if I'm doing it in my diagram, I can just be doing 1.0. Okay. And then, okay. Um, what's next? 1.5. Okay. All right. So this is like, how will I call it? The range, right? Of course, I'm not saying that it's only these three that are there, but you have you understand what I'm talking about, right?
Mm.
Okay, good. All right. So um that's the range. So now if you now want to talk about the codomain will now be all those other numbers that are not what? All those other numbers that are in the set of real numbers, because we use, this is the denotation for real numbers, that are in the set of real numbers, but are not in the range. So you can see there are too numerous to even count. So I can't even represent them because, I mean, I'm just thinking of the space. But you have an idea that there are definitely other numbers here, including, like I said, negative real numbers that are not covered. Okay. So once we understand that, um, we have that concept at the back of our mind, we now know that um, um, the codomain is a huge set, probably, of course, way bigger than the range. But then now, this shows that you understand what's really going on behind the scenes. So I want to know, do you have any questions?
No, sir.
Okay. All right. So let's go back to your notes. Um, Let me go back to your notes. Okay. So she's okay. So I think this is an example. So let's consider this her own example. This is a very simple function, x plus 3. Um, what do you think about this? If you were asked, um, what is the set for the input, what would you say is the domain for the input?
For is it for these questions?
Yes, for this particular one, what would you say is the
One, two,
set?
and three.
Yes. Okay, that's this. That's the domain, right?
Yes, sir.
Now, did you notice something that this question they did not say anything about the set of numbers, but we're just looking at one, two, and three. Can you come to some conclusion that
Mm,
they are natural numbers? Well, at least a subset of natural numbers, right?
yes, they are.
Okay. 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 So, um, and you can see how what do you call it? The range is obtained just by adding three to each one. Um, um, Now, what I equally want to bring to your attention, um, um, let's see, um, what do you call it? The way we write the independent and the dependent variables. Now, to express something, to say something is a function of another thing, um, is for us to uh, use that expression, the f of x. Y is a function of x. Okay, so that f of x is another way of writing the independent variable to say that the inputs are x, represented by x, and then the the function name in this case is f. But what I want you to see is that you can use any letter of the alphabet at all, any letter. But when you get used to that fact, then if you see something like gx, you know that you know it's open to any um, um, letter at all. The important thing is for you to know what the mapping is and how it relates to the particular question you have at hand. Okay, so let's move on. So another this thing there is the expression there for um, the the values of the input versus the output. Okay, all right. So this is like a summary. Domain is the set of all the inputs. The range is the set of all actual outputs, and the codomain is the set of all possible outputs, which means that they are way larger than you know the range. Okay, all right. Okay, so I think this is just helping us to understand some other concepts of functions. Okay. Okay. Uh, intervals. Okay, so when we have a closed interval, we say is denoted by what? Square brackets. Okay. And a value and b value are included in this interval. So this one is quite straightforward. If you remember when I said I was giving you an example of there are infinite set of numbers between 0 and 1. In If you want to talk about 0, 1, 0, 1, and then you put them in between square brackets, right? The square brackets, yes. That is an example of a closed interval, and that would mean that 0 and 1 are part of the numbers that you are counting. So for instance, you can think of it this way. It's not like we can list it all, but at least you can start with 0, comma, who knows what is probably the next number after 0. It can be 0.000001, 0.00025, So it's just saying all the numbers. So what they usually do is just put a comma that you will understand that it's whatever comes after. And then one being the second number in that closed interval means that one is the last member of that closed interval. Okay. So of course, open interval means that it can either be open on one end and closed on the other, or closed on one end and open on the other. So that's just what that side is trying to say. Okay. So um if that's the case, let me see if you can figure this out. For um for this, if we have something like this, uh, 1, 1, 10, where you can say x is element of natural numbers. What would you say is this in the real set?
I was
What would you say is what are the numbers that? Yeah, go ahead.
Like what mean by what like in the set?
So what would be the first element in this one?
One,
One, correct? Yes.
two,
Two, okay.
three,
Three, okay. So now we have an idea of the trend. You can put dots, 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 and then put what will be the second to the last one.
9,
Second to the last.
8,
Are you sure about nine? So
8.
if you say that nine is second to the last, you would be implying that 10 is involved, is included. You know that, right?
Okay. So
Mm-hmm. So that means eight will be the second to the last. And then nine. And the reason why nine is the last one is because this thing is open on one
second to the
side.
end. Yeah, second to the last means like the number before the last number. So,
Yes, exactly. Exactly. Yes. Okay. All right. So I just decided to do that as an, just to test our knowledge. Okay. So, is this an example? Consider the functions below. All right. Where x maps to 2x. So, of course, whenever you see this kind of thing, set of natural numbers to set of natural numbers. Um, Yes, this is just emphasizing that thing I said that you can look at the input side, look at the output side. Some of the outputs don't have anything mapped to them. And we said that if that happens, that is perfectly okay. The only place where there's a problem is when there are some inputs that don't have anything mapped, they're not mapped to any outputs. That's where there will be an issue. So this is a perfect example. X being mapped to 2x. You can see that by the time you start, the first number in the range is 2 on the Y side. That's the output side. There's no there's no one that you can use. Uh, you can map from the input to 1 on the output side. Why? Because it's set of natural numbers. So that means the only thing that could have given us 1 would have been 0.5, and 0.5 is not a natural number. Okay. So that means that 1 is among the numbers that are in the codomain. Okay. And of course, you can see 3 is also there too. So in other words, it looks like we've left out all the odd numbers, and yeah, the odd numbers are the bits that make up the rest of the codomain, while the even numbers I'm talking about the output side, while the even numbers are the range. You can think about it that way. Okay. um yeah. Okay, I think I've even discussed this one when I was explaining it. X being mapped to x squared. X being mapped to x squared. Uh, mm, okay, now can you see how they came up with what the range would be? I want you to look at um, this second example. The domain, of course, is real numbers, right? And that includes negative integers, positive integers, decimal numbers, and negative, positive, all in between. Of course, you can imagine that when you square any of those numbers, did you notice that whether it is negative or positive, the answer will always be positive.
Oh, if I square.
Goodness, did you notice that? Yes, if you square a negative number, whether you square
Oh,
a
yes, it will be
negative,
positive.
yes, it will always be positive. So you can see that the codomain, well, I'm looking at it very well. Now the codomain is what? Is real numbers, but the range does not somehow excludes what they call it. Um, it excludes negative numbers because the square of whether it's negative or positive will always be what? Positive. And so that is why um, um, you can see that the range is saying that minus infinity, negative infinity to 0.25. Okay, hold on. Let me be sure what is really going on there. X squared. Why is it 0.25? Hmm. From negative infinity to 0.25. Oh, okay, okay, okay. I think something is there's a is I think okay, so yeah, it's not it's not um all the real numbers that are involved. I'm just looking at it. X raised to power 2 minus infinity to infinity. 0.25. Okay. I'm not sure. Okay. This guy is looking a bit um, from negative infinity to positive infinity. Infinity squared, of course, that's going to be huge. Um, but I'm just wondering why that 0.25 is there. Did she explain why the this thing is closed on 0.25 but open on negative infinity?
For this old thing, the one in the
Mm,
box, she didn't go through
yes.
that. She just summarized it to the one
Oh,
at the
oh,
bottom.
I
So
see.
because she knows we won't understand the
Okay,
full thing, so she summarized it.
okay, okay. I see. Okay, all right. Okay, okay. I see what she's saying now. Okay, okay. This one is still talking about the 2x. Okay, okay. Well, all right. Okay. Ah, my battery is already out. Okay, so let's see. Let me just see if we can consider this particular question. Is the range equal to the codomain? Of course, for this particular example of x being mapped to 2x, the range is not equal to it. Why? Because it excludes odd numbers. So then it can't be equal to um, the whole codomain, which is the possible outputs, which is if it's natural numbers to natural numbers. So the answer for this question is no. And that's based on our understanding of what's going on here. 1, comma 2, 2, comma 4, 2 being mapped to 4. It excludes all the odd numbers. Okay, so this is the bit that, oh, I see, I can see it now. Minus x squared. Okay, that's the reason why. Okay, it didn't look clear. That was what. Okay, wow. Okay, all right. Okay. Goodness, I was wondering, I'm just trying to see if we can like have, because of my battery, if we can have, can I say, maybe sometime tomorrow. I don't know how your Wednesday
Oh,
is.
tomorrow, for how many minutes?
Okay, we could just do maybe 30 minutes or so.
Okay.
Uh, yeah, just to
Yeah, that's
make it.
fine.
Okay, okay, all right. I think I'll just use that time and explain this other bit. Okay, but at least what we discussed today, you understood it, right?
Yeah, I understand the
Um,
it's just the last.
the basic concept.
Yes, but I understand the start of it. But it's
Okay,
for the last. I think I sent the
so
last thing for the homework.
okay, is it this part?
Yes, sir. The
Where
one
is it?
behind it.
This, okay, this part.
Yes,
Okay, this
the
from
blue
here,
one.
right? Okay, this part.
No, the one down. The
Oh,
blue
okay,
box.
okay, this
Yes,
part.
yes, the blue
Hmm.
box under the no, question 5. Yeah, that.
Okay, this bit.
Yes.
This one that says the following mapping
It's
is given.
question 2 and 3. I understand 1 and 5, just the 2.
Okay, 2 and 3.
Yes.
Okay, okay, okay. But I don't see two. I don't 1 and 5. I only see 3. Or is it maybe because I zoomed out?
Yeah, I've done half of the 2, so I'll just complete it. But the 3, we can do the 3.
Okay, okay. Okay, find the value of B if F1 equals 10. Okay. F1 equals 10. So that means F1 means anywhere we have um 2x plus B.
Hello. 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 Good evening. Hello. Hello. Hello.
Okay, Messi, can you hear me now?
Yes.
All right. Okay, thanks for.
Now I can see. I can see. I can see. I'm on a screen. Oh,
Okay,
good evening.
are you good?
Yeah.
All right. Okay, so Did you screenshot the notes?
Nah, I forgot to get them on accident.
Okay.
It was an accident. I didn't have her today. Mom, I didn't have her today. I forgot.
In Sydney, you're always just having a field day in this room. Can you just do a lesson?
Okay. Oh, all right. Let me see if we can work around this. Hmm. All right. Let me see if I can get those um the the material that we looked at back then in class. Um, it's just I just really wanted us to be sure of
There's nobody you can ask.
the things.
Oh no, I do have it
Where?
in my bag.
No, I brought this is bad. Is there even doing this upstairs?
Sorry, Uncle, I have my book. I forgot.
Yeah. Okay. While it's coming up, let me see. Um,
Mommy, why are you getting angry?
then it's kind of slow. Just let's give me some time. I'm trying to load up. Um, Minutes. Know that we did this. When was that? Yeah, what was that one? It's been a while. Let's see. That was our Saturday class. Yes. Yeah. So we did. It was Dalton's atomic model. Okay. Okay. Atomic model. Yes. Okay. Yes. Okay. Hmm. Okay. Coming up. Let's see. Yes, I think this was one of them that we used. Okay.
Let me quickly check the list again.
Okay. Is that something you want to check with?
No, I was just checking the list again. Okay,
Okay, all
okay.
right. Yes.
Yeah, okay. Dalton's
The
box.
one you sent on the WhatsApp group, right?
Mm-hmm.
Okay. Okay. All right. So I think we can establish some basic things in his theory, Dalton's atomic theory. First off, his first assumption was that atoms are the smallest particles you could ever find, which I'd say
a whole gum in a space of
were
2 weeks.
disputed by other theories. So let's
Already got a whole pack, Noah. What are you talking about?
Okay. Okay, can you see my screen?
Yeah.
Sorry.
Okay, good. All right. So this was his model about, or his concept about what an atom was. Because we need to understand that these were theories, right? And in science, things have to have substance to get to be proved. So nobody could really see what atoms were. So this was his own assumption. So once you have that at the back of our mind, we can go ahead to understand the kind of thoughts or his thought processes, if you like, behind what he was thinking. Okay, so what I think I have. Okay, yes, all right. Okay, so this was the first postulate, which he concluded that atoms were the smallest. Matter is composed of very tiny or microscopic particles called atoms. Okay. Of course, by concluding that an atom is indivisible, that was his own assumption, that an atom couldn't be further broken down, and there was nothing smaller than an atom. Of course, we also see that other models came to tell us that atoms were not the smallest. We actually have smaller particles inside atoms. And then, of course, this one that says atoms can neither be created nor destroyed. I think this particular theory was also challenged with radioactivity, right? Radioactivity, we saw that with radioactivity, you could actually create an atom. And then with the advent of the atomic bomb, that was a massive attempt to destroy an atom. And we saw what happened in the was it the Second World War, I think. That was how the Second World War ended. So atoms can actually be created or destroyed. Now, why am I trying to make it, explain it to you this way? So that you have an idea that Dalton's atomic model was at least a good attempt, but it was not the final attempt at, explaining what an atom really is. Okay, but at least he made some effort, which is the reason why we are even studying it in the first place. And of course, this is the fourth concept being expressed by that same theory, that atoms of an element are identical in size, okay, shape, mass, and in other properties. I think this particular postulate holds true, and you can see that in the periodic table. All atoms of a given element are identical. Okay, of course, that also emphasizes purity in terms of the element. So, for instance, a piece of iron cannot contain, another element. Okay, it would just be iron all through. So they're identical in size, in shape, mass, and other properties. Okay, so all right. Of course, the next one is more like I would say let's say the opposite of the previous one, that atoms of different elements also have different properties. Okay, but we had a small modification to this one because we saw that in the periodic table, some elements are different, but because they are in the same group, okay, they are in the same group, their properties are similar. For instance, metals, right? Metals can conduct electricity. That property alone is something that underscores the fact that they are similar, but they are different. They are different as per their different elements, but because they cannot conduct electricity and heat, okay, those are some similarities in their properties. So they're not exactly totally different. Okay, so that's what we just want to um, say about that fifth postulate. And of course, the sixth one that says atoms combine with each other in small whole numbers. This is what happens when you have a chemical reaction. Okay. Now take note of the phrase small whole numbers. It means that we don't have a scenario where you would have one atom of a particular element combining with 2.5 atoms of another element. No, it will be a whole number. Okay, and once you see this, you will see that this is what makes understanding what's happening in a chemical reaction very um, um, easy. Okay, because if you couldn't establish that it was in whole numbers, then it might lead to guesswork or some kind of calculations that we may not be able to fully arrive at. So just remember that atoms combine with each other in small whole numbers. Okay. All right. Okay, now this is another one that says chemical reactions are due to a combination or separation of atoms. Of course, this one holds true. Why? We saw, I don't know if it was when we were talking about sodium combining with chlorine, right, to give you table salt, the salt you put in food, okay, or maybe your mom uses in the kitchen. That's NaCl, right? Take note of the fact that it's a combination of two atoms or atoms of two elements. Let me put it that way. Of course, you understand what I'm trying to say. NaCl. Now, what do we mean by separation of atoms? So, if you have a compound, I'm not sure you've probably seen an example like that. But instead of them to combine, it's one compound, okay, but it's made up of several atoms. Instead of it to maybe it's heated. If it's heated, sometimes they don't happen by themselves. But when you heat them, they break down to their individual atoms, okay, plus some energy is released. That can be said to be separation of atoms, okay. So remember this, chemical reactions can be due to a combination or a separation of atoms. Whichever is the case, a chemical reaction has occurred. Okay, so of course you would come to see all that. Now, I'm not sure if you guys consider this, but me, I think with just what we've discussed so far, we've somehow seen the limitations of the atomic theory. I told you it wasn't perfect. Dalton just made an effort, which we still study today, because some of the assumptions that he had in that theory were shown to be true, even in chemical systems today. But then, of course, these are some of them which I've already mentioned. There are subatomic particles. Of course, you know them, electrons, neutrons, and protons. So that means that atoms cannot be considered indivisible because they're actually smaller particles inside them. And what next? Okay, I didn't even mention this one, but you can look at this one and consider it. atoms of the same elements are not exactly similar in all respects. They may vary in mass and density, but they have the same atomic number, but different atomic masses. So they are called isotopes. Okay, so for example, chlorine has 2 isotopes. When you might not understand what isotopes are, but just know that they exist. Okay, for the purpose of our class. Okay, they have mass numbers 35 and 37, but guess what? They are they have the same atomic number. And I told you atomic number is the number of protons, not the number of electrons. Okay, and there's a reason for that, because the number of electrons can change based on how the atom is, combining in a particular type of bonding. But the number of protons will not change. So that's why it's safe for us to stick with number of protons for atomic number. Okay. I think these are other limitations. Atoms of different elements are not different in all respects, because atoms that have there are atoms of different elements that have the same atomic masses. We can just take note of that. Then different elements combine in simple whole number ratios. Okay, so there are some exceptions, but you don't need to worry about those exceptions. They are really not too considered under inorganic chemistry, which is the area where you are. And finally, the theory fails to explain the existence of allotropes. Okay, so do you have any questions on this so far?
Yeah, because like I don't really understand it that much.
Which one? The
Like,
limitation. You can leave off the limitations. It's the postulates that you may need to
yeah,
take note of.
the
Do you
post.
understand the postulates?
No, not really.
Okay. Let's see. Let's go. Which of them? I start with postulate 1. Which of them? Do you understand the first one?
Yeah.
That matter is composed of very tiny or microscopic particles called atoms. Okay. How about the second one?
Yeah.
Okay. Let's go to the third one. How about
Yeah,
the third?
I understand the third one.
Okay. Fourth. How about this one?
You know when it says atoms of an element are identical, do they just mean one singular element?
Yes.
Okay, yeah.
Yes, it's talking about one singular element. Now, yeah, okay. So when you look at it in that regards, that's why I gave an example. I used iron. You remember when I was explaining this, I used iron as an example, right? They are identical in size, shape, mass, and in other properties. And what this means is that you can now I want you to listen carefully to what's the implication of this. You can only find one type of atom of iron, for instance. You can only find one type of atom of chlorine, for instance. And then let's even look at carbon. You can only find one type of atom of carbon. Okay. But if you later come to see, that even with a particular element, you could find atoms that are not exactly identical based on their mass. Okay, so that was why in that example I told you that there are atoms that are of the same element that have different mass. Okay, but they're the same element. You know why they're the same element? They have the same atomic number, but they have different masses. Okay, but usually the masses are not too far apart, like that. But then remember, this is just a postulate of Dalton's atomic theory. So let's just understand it like that. Okay. So you got this covered, right? You're good with this, right?
Yeah.
Okay. Okay, so how about this next one? This next one is like an implication of the previous one, that atoms of different elements are different in their properties.
Yeah.
Okay, so you understand where this would play out. Atoms of iron will definitely be different from atoms of chlorine, even both, whether it's the physical or chemical properties, they are different, they behave differently. Okay, how about this one?
No, could you explain it?
Okay, all right. So atoms combine with each other in small whole numbers. Okay, so I'm going to use, let me just see if I can use an example to explain it. Okay, I may need to, or should I just annotate? Okay, let me annotate. Let's see if I can annotate. Here we go. Nah, this guy is acting up. Okay, I may need to share my screen. Give me a minute. Let me share my screen. Okay. All right, nice. Okay. Okay. Um, okay, so let me use this as an example. So I think we have talked about carbon dioxide before, right?
Yeah.
Uh-huh. So this was a typical reaction that could happen with carbon dioxide. C plus CO2 would give you CO2. Okay. All
Okay.
right. So this is a very simple example, right? Atoms combine with each other in small whole numbers. So you can think about it this way. Even though I didn't write it, but it's clear that this is one atom of carbon. And it's combining with, careful now, 2 atoms of oxygen. How do I know that it's 2? Because of this 2 that's here. Okay. And why is it like that? Because oxygen is a gas, and gases usually combine as molecules. They usually hang out together. So 2 atoms of oxygen will be found in 1 molecule of oxygen. Okay. So that's why it's like this. So I can't come and put a 2 here and say, no, it's going to mess things up. Okay. So this is it. 1 atom of carbon is combining with 2 atoms of oxygen to give us carbon dioxide. Okay, so you can see it agrees, isn't it? Small whole numbers. So you understand the concept now, right? Okay, so that's the explanation for that. For that one. I'm trying to, okay. All right, let's go to the next one. Let me erase this so it doesn't mess up our work. Okay, so sorry, this thing is, so okay, sorry, let me take it easy. Combine with each other in small whole numbers. The next one says all chemical reactions are due to a combination of or separation of atoms. I think this one, the explanation I just gave you for that last one also somehow agrees with this. Okay. 1 minute. Okay. So all chemical reactions are due to combination or separation of atoms. So based on what I explained in that previous one, would you say you understand this one?
No, not really.
Okay. Combination or separation of atoms. Let me explain it again. Carbon combines. What's happening? Stuck. Just give me a minute. I don't know. My computer seems to be on the hanging side today. Okay, it's back. Okay. Okay, so carbon combines with oxygen, like I said, to give us what? CO2. Now, this is a combination. So let's see the reverse, where it's talking about separation of atoms. A good example of separation of atoms is what happens in the atmosphere when we were talking about acid rain in the atmosphere, that H2, CO3, you know, because it's possible for it to break down to give you what? Water and
Is
carbon
able to
4 yes, yes, plus carbon dioxide. So this is a possibility, and this could be said to happen maybe during some during rainfall. This could happen, right? So yes, if this happens, then you can confidently say that this chemical reaction is a case of what? Separation of atoms. So it's not as if all the atoms separated entirely and they are now standing on their own. No, but somehow there is a kind of breaking of the bonds between some of the atoms, right? That now led to them separating into two compounds, water and carbon dioxide. So do you understand what he was trying to say by separation of atoms?
I think so.
Okay. So I think if you have this picture at the back of your mind, this example at the back of your mind, you remember. Okay. Okay. Let's see. Okay, I think that's the last one. Okay, so let me see. So that was his those were the assumptions under his models. Okay, so let's look at the would I say the model that we've all come to really embrace, which led to the periodic table that we all know today. That's Mendeleev's table. So it's with that we will this talk about chemical properties, and then what you might call physical trends and chemical trends. Okay. All right. So let me see. So I'm going for Mendeleev now. I hope I'll be able to. Let me just try and see if I'll see material. Mendeleev's table. So we know Mendeleev's table is just us trying to be specific about who actually, oh, really? Thank you for that. Okay, all right, so it's popping up now. Okay, so I know I explored one that last time that we discussed, but I don't want to go back to that particular one. Let's see. Um, uh, where are we? Where are we? Where are we? The development of the periodic table. No, we don't want the development. We want to see. Okay, this is quite great. I like this one. This one is quite colorful. 40 slides. Let's do this one, 22. Okay. All right. So, yes. So this how I like this particular periodic table because it's kind of annotated, well annotated with colors. And those colors help you to see the ones that are similar in behavior. Okay. You can see those blue ones, the blue ones in the middle, the sky blue ones, not the ones that look like cyan in the middle, right? Those ones are the transition elements. Those guys are in a world of their own somehow, because I mean, they like break rules and make rules. Those are the privileged few among all the elements in the periodic table because they are really, really special. And it's as if they are on their own, in terms of chemical properties and even sometimes physical properties. They have special ways of, interacting with other elements. So they're in a class of their own. Okay, so let's look at okay, and of course, the ones that are called non-metals, right? Uh, those ones in green, boron, carbon, nitrogen, oxygen, silicon, phosphorus, sulfur, excuse me, and the rest. Okay, now, fluorine, chlorine, bromine, and the others, those ones too are non-metals. But I think because they are in a particular group, it's safe to give them a particular name. That's why they call them halogens. Okay. Well, yeah. I'm not sure if they want you to know the group name, but it's not. It doesn't hurt to know them. All right. So let's look at the first group. Now, if you look at the first group, it starts with hydrogen. Now, you'll be wondering, why would hydrogen be sitting directly on top of metals? Because you have, under hydrogen, you have lithium, sodium, potassium, yes, and the rest. Now, you see that all those guys are metals, right? So would you class hydrogen as a metal? No.
No.
It's not. It's not. It's actually a non-metal. That's why you see it has the same color notation as the ones that are in green on the right-hand side. Okay. So I just thought to say that for clarification. Okay. So a lot of thought and planning, I would say, went into developing that periodic table. So you can see what do you call it? The things that govern it, right? The periodic law that states that repeating chemical and physical properties of elements change periodically with the atomic numbers of the elements. Okay, so this is just the general law, all right, that governs the periodic table. Okay, now if you want to talk about physical properties, right, we start with metals. These are the general properties. Did okay. Do we want to go that way? Okay, that's fine. Now, I was asking you in the last class, right? Were you
Mm.
expected to memorize the elements, the first 20 elements of the periodic table? Were you expected to be able to memorize it?
I think
Memorize.
so.
Okay. So have you been able to come up with an acronym that you could use to remember them? It's really more like a personal thing. That's once you can develop something that you can remember, it will stick with you for life. Okay.
Mm.
Like I said, we back then we had a song, but I can't remember the song myself. But it's I know that the one that sounded more like a story stuck. Let me see. Is this something I can decode now? It was really interesting to memorize it back then. No, 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 no. I can't, I'm not sure I can even recall the story now. No. I know that we had to. Okay, so the first 20 would be from hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. Okay, because I think that it's safe for us to just memorize those because after that you now start having the transition elements, which like I said, they're in a world of their own. Uh, okay, okay, so uh, okay, so I think we've said a bit about metals, right? That metals have physical properties, we know. Typically, they're shiny, they conduct heat, energy, and what? Electric current, right? And I think when we studied properties of metals one time, you remember that we said they could conduct electric energy, electric current because of the free electrons in their atoms, right?
Mm.
The electrons were free to move. Okay, not that they could leave the atoms, but they were free to move. So that means that because of that freedom of movement, that enabled them to carry, or as we say, conduct an electric current, carry charges, electric charges. And why for heat, the reason was that they were closely packed. So one atom, when you heat it up, and it's at a higher, it has a higher temperature, and it's close to another one that may be of a lower temperature. Because of that closeness, it transfers the energy to the next one that's close to it, and they just keep on going on like that because they are packed. Okay, I'm not sure we have talked about malleable, right? Do you have an idea of the meaning of the
Is
word
is
malleable?
malleable? Is it like something that can be bendable?
Yes, 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 correct. It can, yes. So, yes, as opposed to being brittle, like if they can't bend, that means any attempt to bend a brittle, something that's brittle, it will break. Okay, but yes, metals are not like that. They are malleable. Okay, so I think there's some what do you call it? Sometimes there's confusion between um malleable and there's another term, but maybe let's leave that one for now. Let's look at the one that comes before malleable, ductile. Okay. So you have what do you understand by the term ductile? You understand that?
Is ductile like strong?
Like a string. Did you say a string? I didn't get you there.
No, I said like strong.
Okay. Okay. Let me see if we are talking about the same thing, right? You could draw them out into a thin wire. Okay. And they wouldn't lose their toughness and they wouldn't break. Okay. So of course, something like copper that's used for making wires.
Wires.
Yes, fit would fit in that category, right? Okay. Okay. Other physical properties. They are solids at room temperature. Of course, you know that there is one metal and that one is not really, like I told you, they have their own, a word of their own, transition elements. Mercury, okay? Mercury can go for a metal, right? Mercury is a liquid at room temperature, but let's see why it is even classed in that category. If you look very well, the chemical symbol for mercury is H. Sorry, just give me a minute. Let me see if I can find it here. Yeah, Hg, yes. Okay, so you can see it there. It's somewhere at the bottom, at the sixth row. Okay, and 1B. Okay, the sixth one is in red. So it's a transition element, and it has some kind of peculiar behaviors which make it possible that it's a liquid at room temperature. Now, does it now mean that there's a temperature that you could actually make mercury to become a solid? Yes. All you need to do is to keep on reducing the temperature. Just, if you like, freeze, you can call that freezing, right? Freeze it to a point that it can, you keep on dropping its temperature. Once you keep on dropping its temperature, it will become solid, more like solid. So, but then before it happens, before it gets to that, it will take a while. And that's the reason why we use mercury for thermometers, for the liquid inside the thermometers, to make a very good thermometer liquid. Okay, so of course, you can see examples there: copper, lead, tin, etc. Okay. All right, so physical properties for non-metals. As far as we know, non-metals cannot conduct heat nor electric current, which makes them very good for an application that needs insulators. And if that's the case, then it means that they still have their own use, because they can't conduct heat or electricity and electric current. Then they are used for safety equipment, okay, where a lot of maybe high voltages are involved. So you need to ensure safety. So you have insulators in the setup. So what are some of their properties, physical properties? Most of them are usually gases at room temperature, and you can think of them as they are the opposite of metals because of that not being able to conduct heat or electric current. Then dull in appearance. Well, I didn't talk about that, but if you remember when we talked about metals are usually shiny. So by default, the flip side, non-metals are dull in appearance. You can look at carbon. If you look at the insides of a pencil, right? Even though they call it lead, it's not lead as in lead, the metal lead. It's actually carbon, a form of carbon that is inside the pencil. You can see it's dark, it's black. So that's one of the ways that it lines up with that physical property. Examples of non-metals: iodine, sulfur, neon. All of them are gases at room temperature. Neon is an example of what they call a noble gas. Yes. Neon and the others.
Wait, what group
Yes.
numbers is noble gases? Are they like 0, 18, or 1 or something like that?
So the noble gases, right? Yes, that's it. The very last group, you have it.
Yeah, so it's the group 0.
Yes, it is.
Oh, okay,
Yes,
okay.
yes. So they are, I think it's also safe to say that they too are in a world of their own. Now, the thing about noble gases, right? An element in that group is that they don't usually like reacting. Okay. And why is that? Why do you think that is the case? Can you guess?
You want to use it right now?
Pardon?
Can you guess why they don't usually like reacting? As in they are usually stable. They don't, if you when they occur naturally, they don't usually like reacting with other elements.
I'm not sure.
Okay. Now, if you remember, right, when we looked at Mendeleev's the atom, right, based on atomic number, we saw that after the first ring of electrons, right, the first ring of electrons around the nucleus would hold 2 electrons, right?
Pardon?
Okay, don't worry. Let me just draw it so that you remember. You can still see my screen, can you?
Yeah.
Okay, please, I just need you to, this is more like I would say, reminding you of what we had already done. Okay, so just take a look at this. I want you to think of this as the first row of the inner circle. There is the nucleus. I'm not drawing what is inside the nucleus. I'm only drawing what is around the nucleus. All right. Then look at 2. This is an electron. Okay. Because electrons usually occur in pairs. Okay. And this is another electron. Okay. So this simple thing I just drew now is the representation of helium. Is it helium? Yes. This is the representation of helium, because helium, the atomic number is 2, right? Now, so I remember that helium is what? It's also a noble gas. It's part of the noble elements, right? Now, if you take a look at what I think is one of the rules, it says that every element that has either 2 electrons in its outermost shell or 8 electrons in its outermost shell already doesn't aspire to get anything more. Okay, take note. Either it has 2 or it has what? 8. It doesn't usually want to, react with any other one. Why? Because they have achieved what is called the stable configuration. It's like they are, that's why I said that they are also in a class of their own. They don't need to react. But guess what? Any other element that's either slightly above 8, so let's imagine an element has 9 electrons in its outermost shell. What will it be doing? It will be looking for how to shed 1 electron so that it will become what? So that it will become 8. Okay. While the guys that are either that are maybe less than 8, like say 7, right? 7, the ones that have 7 electrons will be looking for how to do what? To gain 1 electron so that they will become what? They will have 8 in their outermost shell. Do you understand?
Yeah.
What did you say?
I said yeah.
Okay, so if you understand how reactions, how elements usually behave when they are reacting, some of those chemical formulas, some of those reactions, you would understand them completely. Okay, so I think that was where we now start talking about ionic bonding and what other type of bonding, covalent bonding. Okay, so some elements share and some give away, completely give away, while some they don't give away, they share. Okay, all right. So yes, I just thought I would say that because we came across neon, which is an example of a noble element. Okay. All right. So these guys are quite different. So notice that these ones are they are called metalloids. Why? Because they have properties of both metals and non-metals. Okay, so you can see them: boron, silicon. Is that germanium? I'm not too sure now, but all those ones that are down there, right? Polonium and the rest, they fall into that category of metalloids. Again, the meaning is that they have properties of both metals and non-metals. All right. So boron, silicon, antimony are, examples of that. Okay. So let's see. Let me see if we should. I'm looking at what you shared on the group. If we need to talk about um, ionic bonding. Okay, so we discussed what happens, the trends that happen down a group, right? And the trends that happen across a period. Okay, so which of them do you understand very well? The trends that happen down a group versus the trends that happen across a period. Which of them do you understand very well?
I think the ones that happen down the group.
Down the group. Okay, so if you look at what we have in front of us here, a group is a vertical column of elements on the periodic table. So they have similar physical and chemical properties. That's why if you look at what do you call them? Even from the first one, the ones that we said are metals and that have hydrogen somehow sitting above them. These guys are, they have similar physical and chemical properties. Okay. So let's see. Okay. It's the trends that I'm looking for now. Just give me a minute. Let me go to where the trends are. Okay. Okay. I think okay. Okay, the periodic table and chemical bonds. Let's see. Okay. I think this is more like it. Okay, so I want to quickly talk about the trends, right? That we can find in the periodic table. Trends. Okay. All right. So you can still see my screen, right?
Yeah.
Okay. You can see my screen.
Yes.
Okay, all right, good. Okay, so the first trends that you can see, like I said, when you move down the group from top to the bottom of the table, and then across a period from left to right, that's on a particular row. A row is, considered as a period, while a group is considered the vertical um, class, okay, of elements. Okay, so no, it's not valency I'm after. Okay, yes, let's start with atomic size. All right. So remember this, atomic size refers to the radius of an atom. What happens when we're talking about atomic size? It's also the distance between the center of the nucleus of an isolated atom to its outermost shell. Now, remember, the outermost shell is the shell where you have electrons that can easily move. Okay, so that let me put it that way. They are available for combination or sharing with other atoms. The ones inside are not available. So remember that. And you can even think about it this way. The nucleus, which contains protons, is exerting an attraction, like a magnetic pull. I don't want to use the word magnetic, but you understand what I'm trying to say. Positive attracts negative. Okay? So the protons inside that are concentrated inside the nucleus are doing what? Pulling on the electrons that are immediately around it. That's the reason why the ones that are around the nucleus don't usually want to react. They don't want to participate in reactions. It's the ones that are on the outside, that are further away from the nucleus. Those are the ones that the pull, the attractive pull, is not really strong on them. So that's why they can be involved in a reaction. So let's look at the trend for atomic size. Atomic size, as like I discussed the last time, it increases downwards. So take a look at this. I want you to see this trend here. Lithium is greater, leads to beryllium. In other words, beryllium is bigger than lithium. That's what that thing is saying. Okay, from hold on, is it okay? Oh, okay, sorry. Across a period it reduces, but down, okay,
It's
down a
increasing.
group it increases. Yes.
Yeah.
So please, yes, let's not mix it up. This actually across a period. Atomic size will do what? Reduce across a period, but down a group it increases. Okay. All right. So what would we say is the implication of that? well, it will mean that those ones that have bigger atomic sizes are more willing and eager to react. In other words, they have higher reactivity. Why? Because the electrons at the, in the outermost shell are further away from the nucleus. So those guys are freer to move and react, if you like. Yes. Okay, so that concept I just explained now, do you understand how it works? Do you understand it now?
No, not really.
Okay, let me use an example. Let's quickly use an example. Going down a group. So look at the trend for going down a group. Lithium's atomic size, is less than sodium's own, which is less than potassium's own, which is less than, I don't know what that RB, I can't remember that FR. Okay, so, but let's see if we can explain it. Yeah. So potassium is more reactive than sodium, and sodium is more reactive than lithium. Okay. So then let me see. One of them can react just by exposing it to air. You hear a pop sound. Okay. And that means that it's heavily reactive. Whereas the ones that came before it, like sodium, okay, sodium would not be so reactive like that. So let me see. Because of the, yeah. Okay, so let me see if I can draw how it would look, right? Okay. So lithium is Li, I think that's 3. Okay. So lithium looks something like this. Lithium looks something like this. 2 electrons in the shell around the nucleus, and then 1 electron out in the outermost shell, right? Now, sodium is 11, so that's going to be in the shell that's directly around the nucleus. There are 2, okay, plus 8. Plus 1. So that's how we get 11. 2 plus 8 plus 1. So remember that formation. 2 plus 8. So let's put 8. That's 2, 4, 6, and then 8. Okay. All right. Can you see what I just drew now?
Yeah.
Now I want you to take a look at this. This one that I'm still drawing now is what? Sodium. You can see clearly that even the size, the atom even looks bigger, isn't it? Now, what I was saying is that there's a pool, right? A pool, that darker circle in the middle is the nucleus. That is where the protons are. And the protons are always have this strong attractive pull, okay, on the electrons. Why? Opposite charges attract. It's a fact. Okay, just remember that fact. opposite charges attract. That's how they happen. So these guys, the first, what do you call it? The first circle of electrons, which is the two, the ones that are two, those ones have the strongest pull on them. So this guy, sodium is not, the sodium nucleus has a very, very strong pull on it. So those ones will not even go into any reaction at all. They can't be shared, they can't be given away. Then the next one are the ones that are 8 around those two that are very close. Those ones too, there's a strong pull on them, so they don't usually leave like that in a reaction. But guess what? That last one that is outside, because sodium is 11. Always remember the atomic number is 11, and somehow the atomic number is the number of protons. But guess what? In an atom, the number of protons is equal to the number of electrons. So that's how I know that I also have 11 electrons in sodium. So the one that is in the outermost shell, that single one that makes it 11, is further away from the nucleus than the first two, than the second ring of 8, okay? And because it is the farthest away from the nucleus, guess what? The pull on it is not so strong. Did you get that?
Mm-hmm.
So that means that sodium is more reactive than lithium. Why? Because that one that is in the outermost shell is farther away. And guess what? Because it is farther away, it is freer to move. So you see that sodium is, if it's on its own, it's that one that is in the outermost shell is freer, and it will quickly want to do what? React with another element. So that's why sodium chloride happens quickly too. Sodium too can quickly react with water in the air. I think it's the one that it says makes a pop sound as it's reacting with cold. It can react with cold water. Okay. Why? Because it's highly reactive. All right. And again, I said that is because of the distance of that electron from the nucleus. Okay, so you understand that concept now, right?
I think so, yeah.
Okay. All right. So let's quickly explain the other trends. Oh, sorry. Let me delete that. Okay. Okay. So this one is ionization energy. And I think I've indirectly explained it because of that. Look at the definition. The amount of energy required to remove the outermost electron from an atom. So based on my explanation, right, maybe I should even go and put that guy back. Based on my explanation, which one do you think has a higher ionization energy?
Is it sodium?
Okay, now hold on. Just hold on. I want you to reason this thing together with me. Let's be on the same page. Let's look at the meaning of ionization energy again. Ionization energy is defined as the amount of energy required to remove, in other words, to extract it, to remove the outermost electron from an atom. Now, the question that I asked again, I want you to answer it correctly now. Between sodium and lithium, which one would need a higher ionization energy?
Lithium.
It's lithium. You know why? Because its outermost electron is closer to the nucleus than the outermost electron of sodium. Okay,
Mm-hmm.
so that's the reason why. So in other words, it means that down a group, as atomic size increases, ionization energy will reduce. Does that make sense?
Mm-hmm.
So that's what we're expecting to happen. And if you check it, that is the trend. On going down in a group in the periodic table, a new shell of electron is added. That's what I just explained, but without my diagram. And which causes more screening and of the outermost electron from the nucleus. Okay, in other words, they are saying that the outermost electron is farther away. That's another way of saying it. So the atomic size increases and the force of attraction between the outermost shell electrons and the nucleus of the atom decreases. Thus, the ionization energy does what? Decreases. Okay, so once you understand this basic concept of atomic size, you can use it and explain anything when it comes to trends. All right, so yeah, you are right when you said that the ionization energy of lithium is greater than that of sodium. You can see it there. Okay,
Mm-hmm.
of course, the opposite is somehow the case when it comes to from left to right in a period. Why? Because the atomic size across a period from left to right actually does what? Reduces. And so since it reduces, since atomic size reduces, ionization energy will increase. Remember, ionization energy is the energy required to do what? Remove the outermost electron in an atom. Okay.
Mm.
So you can see the flip of that is also true. Okay. So this one, I don't know if we have discussed it. Metallic characters. That's the tendency to do what? Tendency of an atom to lose electrons is usually a strong property of what? Metals. Okay, don't forget that. It's the tendency of an atom to lose electrons. Metals usually like doing that. Why do they lose electrons? I mean, if you look at it from what I explained back then, you see the reason why. Look at lithium, for instance. If lithium loses that outermost electron, how many electrons will it now have in its outermost shell?
2.
Thank you. And remember that time I told you that elements usually do what? They struggle to do what? I don't want to use the word struggle, but I'm sure you have an idea of what I want to say. They aim at, yes, let me use that word. Their goal, ultimate goal is usually to do what? Have an outermost, what do you call it? An outermost shell that has 2 electrons or 8 electrons. So if you look at lithium, that is why it's like that. And if you look at sodium too, it has that tendency to do what? Give away that outermost electron so that it will have 8 in its new outermost shell. Let me put it that way. Okay. So yes, that's a metallic character. So we are saying that that characteristic, that metallic character, along a period from left to right, what will happen? Metallic character will decrease. Why? Because atomic size does what? Atomic size decreases. Okay. Always remember, when atomic size decreases, it means that there's a stronger pull from the nucleus on what? The outermost electron. And because there's a stronger pull, if there's a stronger pull, don't you think it will be harder to give away that outermost electron?
Yeah.
Exactly. That's the whole idea. So some of these things, if you think about it carefully, you will arrive at the right answer. You don't even need to start cramming anything. I always tell people that who cram, if you can't find a way to memorize something, you might run into a problem when the facts are twisted or changed a bit. So if you can reason your way out, you would always come out, good all the time. So yes, across a period, that's what happens. But of course, you know what the drill is. Down a group, atomic size increases. Therefore, the metallic character will also do what? Increase, because it means that the strength of the attraction on that outermost electron gets weaker and weaker and weaker as atomic size increases. Okay, so that means um, the metallic character will definitely do what? Increase as you go from top down in a group. Of course, you can guess that non-metallic character is the opposite of metallic, and so it will be the flip of metallic. So that one, if you can explain metallic, you can definitely explain non-metallic. The tendency of an atom to gain electrons is just the direct opposite. Okay, it makes sense. Along a period from left to right, non-metallic character increases. Why? Because there's a stronger pull from the nucleus on what? Electrons, in the outermost shell. So when there's a stronger pull, what do you expect? It will have a higher tendency to want to collect electrons, not give them away. And that's how non-metals behave. Non-metals will struggle to do what? Collect electrons. Why? Because they want to also achieve that that stable configuration where they have 8 in their outermost shell. Take for instance, consider chlorine. Chlorine's atomic number is 17. Yes, it's 17. So that means that chlorine looks something like this. 2 electrons in the shell around the nucleus, 8 electrons in the shell around the nucleus, and what? 7 electrons in its outermost shell. Can you see? 7 just needs 1 more to become what? To become 8, isn't it?
Mm-hmm.
So do you think, can you see that instead of chlorine to try and give away this 7, what will it do? It will rather take 1, because it's easier for it to take 1, right? And become what? 8, than for it to give away 7. So in other words, chlorine is a strong non-metal. Let me just put it that way. So if you understand it that way, it's better. So it will rather take on 1 electron so that it will now achieve that golden configuration, that stable configuration of having 8 in its what? Outermost shell. Therefore, it's a strong non-metal and it has strong non-metallic character. And you can also tell that its atomic size is definitely smaller than a typical metal, so that it can achieve that feat of being able to attract electrons rather than give them away. Okay, so did you get that concept now for non-metallic character?
Yeah.
Okay. Again, you can reason your way out. It's very straightforward. From left to right, atomic size does what? Reduces. And as atomic size reduces, non-metallic character does what? Increases, because of the stronger pull of the protons in the nucleus of the atom on the electrons in the outermost shell. There's a stronger pull. And so it will look for a way to pull electrons to it to make it stable. All right. So that's for non-metallic character. Of course, moving from top to bottom in a group, non-metallic character will reduce. If metallic character increases, therefore non-metallic character will reduce from top to bottom. Just understand this, because one is the reverse of the other. Okay, so I think this is the bit that has to do with what do you call it? Chemical activity. I think I've explained this one somehow. Chemical reactivity increases down the group because of the tendency to lose electrons, right? And then in non-metals, chemical reactivity decreases down the group because of the tendency to gain electron decreases. Yes, that is a fact that we have. Of course, okay, I don't think I explained this one, but I mean, you can make sense of it if you understand what it means. Electronegativity is what? Is the tendency of an element to do what? Attract the shared pair rather of electrons towards it in a covalently bonded molecule. Okay, so if you, I don't know if you remember when we were talking about covalent bond, that there's usually a sharing thing. Okay, electronegativity is the tendency that the element has to attract it. And of course, you can guess that non-metallic character of an atom is what helps it to have a higher electronegativity value. Okay, all right. So because it wants to attract rather than repel or dash away, give away rather. Okay. Okay. So all right. Okay. So this, I think this is a summary of the trends. Do you want to do a screenshot?
Yeah.
Okay, so wait, let me move this guy up a bit. Can you see it better now?
Yeah.
Okay, all right. So you can do a screenshot so you remember.
Okay, I've taken it.
You've done that, right? Okay. So the reasons there are, it's kind of self-explanatory. So they will guide you when you're recalling it. Okay. And I think these are trends, more trends. Maybe you might want to also screenshot this. Sorry, let me wipe this off. The drawings. Are you done?
Yeah.
Screenshot. Okay. 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 Oh my God. Come on, behave yourself, my friend. Okay. Okay. Can you still see my screen?
Yeah.
Okay. Sorry, my battery is is now low on this one. But I think we're done. We're almost done already. So at least we were able to make good use of the power. Okay, so, and I think this is the last one. Variations of periodic properties in a group. You might want to also do a screenshot of this.
Okay. I've been done.
Okay, good. Okay. Periodic. Okay. Okay, these ones are implied. They're implied, so I don't think you might need to also do this. It's fine. Okay, that's it. Take a look at this one. Do you think you need to screenshot it?
Yeah. I'll screenshot it.
Okay. All right. Okay, so I think we are good to go. All right. So you'll be having the test tomorrow, right?
Yeah.
Okay. That's fine. All right. So I'd like to know how it went. Maybe before Friday if possible. But if not, then we'll just get to know on Friday, hopefully.
I wanted to ask if
Yes,
we could have
yes.
a lesson tomorrow because I have another Friday test. I mean, I have another
Which
test on
one?
Thursday for math.
Okay, in math.
Yeah,
Okay. The same topics that you guys had covered or a different set of topics.
different.
Okay. All right. Will you remember to get the notes for that one? Because I'm not sure you've
Yeah, I will get it.
okay. So once you get it, please share it on the group so I could take a look at it before the class.
Uh,
So you're having that one when? On Thursday, right? Or Friday?
Thursday.
Thursday. Wow. Hmm. My Okay, let me see. I'll try and work something out. I'll let you know. If yeah, 7:30 will be fine. Okay,
Okay.
so yeah, have a good night rest. I wish you the best in the test tomorrow.
Thank you, Uncle.
Okay, you're welcome.
Bye.
All right, good night.
Good night.